Hi, everyone. Let's talk a little bit more about stoichiometry. You know those calculations involving chemical reactions? Okay, so this video, I would like to cover limiting reagents. It can be a little tricky the first time you see these calculations, but I think if we relate them to a cooking example, being in the kitchen, that might be helpful in figuring out how this limiting reagent problem works. Okay, so let's start there. The analogy that I'm going for is that a balanced chemical equation is like a recipe, right? The balanced equation says you have so many moles of reactants and they will make so many moles of products. That's a recipe in the laboratory. So here's another recipe. Let's make some yellow cake. So grab a box of cake mix, flip it over on the back. It says, well, all you need is 1 cup of water. Come on, pen. A half a cup of oil and 3 eggs. Okay, so let's write out the recipe and think about what limiting reagent is in this particular example. So let's first define it before we go into the problem. The limiting reagent is simply the ingredient or the reactant that runs out first. So here's what's happening in the lab and in the real world is that, yes, you can sometimes do very careful measurements and precisely add the exact amount of reagents that you need to do a chemical reaction. But it turns out you don't have to. You could be a little bit sloppy and add a little bit of extra of some of the reactants, and the reaction will still work. You'll just have some leftover reactants at the end. Why would you do that? Because that sounds like wasting. Well, we'll look at kinetics. That's a fancy word, meaning we're going to look at the speed of reactions. And it turns out you can speed up reactions if you tend to use an excess amount of reagents. If you use extra, it kind of drives a reaction to make products faster. So that's one reason why we might want to use an excess of reagents rather than using the precise amounts required by a balanced chemical equation. Okay, so a limiting reagent just puts a limit on how much product you can make. So if you think about it, it's a good word, limiting reagent. It simply means which reactant is going to run out first. Okay, so let's write out the recipe here. What's the recipe? You need 1 cake mix, 1 box of cake mix. You need a cup of water. You need a half a cup of oil. And the last ingredient are 3 eggs. Okay, you gotta watch your cholesterol there. I heard you can substitute applesauce for the oil too. I don't know what you substitute for the eggs. Maybe use egg whites. Anyways, if you want to be healthier. We're talking dessert here. How healthy can that be? All things in moderation. Maybe don't eat the whole cake at one sitting. Moving on. Here's our recipe. And now I want to turn it into a limiting reagent problem. So let's pretend that, hey, my church or volunteer group, whatever, is going to have, I don't know, a bake sale, or they're going to have a little, maybe there's going to be, I don't know, a garage sale or some fundraising event. We have a cake walk. And so I want to donate as many cakes as I can. Or maybe I'm just really hungry for dessert. I want to know how many cakes I can bake out of what I have in my kitchen. Whatever you want to make up here. Here's the idea. The recipe for making 1 cake. Ooh, those are the ingredients. Let's make it look like a chemical reaction. Reagents are 1 cake mix, 1 cup of water, half cup of oil, 3 eggs, and turn that into 1 cake. That's the product, 1 cake. Okay, and then my question is, I want to make as many cakes as I can with whatever I have in the kitchen. So I go through my cupboards, go through the refrigerator. This is what I find. I have a half dozen cake mix boxes. Cool. Got a kitchen faucet, lots of water there. I dig around, I find 4 cups of oil, cooking oil, and then I have a dozen eggs. So how many cakes can I make? can I bake? I want to use up as many ingredients as I can. Okay, well, it's pretty straightforward, right? You would say, okay, let's take them one at a time and assume that all other reagents, all other ingredients, reagents are in excess. We have plenty. And let's just go one at a time and say, okay, what if I run out of cake mix boxes first? We have a ton of water, ton of oil, ton of eggs. That's the assumption. How many cakes can a half dozen cake mix boxes make? Check the recipe. You need one cake mix for one cake. It's a 1-to-1 ratio. So you can make a half dozen cakes, which is 6, right? A dozen is 12, half a dozen is 6 cakes. If we only look at the number of cake mix boxes, we can make 6 cakes. Cool. If we look at only the water, we say, okay, we have so many other reagents, the water is going to run out first. We have lots of water. They haven't, as long as we don't have a drought and they shut off my water, I pay my water bill, I can make as many cakes as I want if water is going to run out first. Okay, that's kind of ridiculous. Water is not the limiting reagent here. It's not going to put a stop onto how many cakes I can make. 4 cups of oil. Okay. Well, it says a half a cup of oil can make 1 cake. So what if we multiply both sides by 2? If we had a whole cup, that can make 2 cakes, right? In 1 cup, there's 2 halves. A half a cup of oil is required to make 1 cake. So I can make 2 cakes here. And then finally, if I have 4 cups, well, multiply both of these by 4. I don't want to draw this. I guess 4 cups can make 8 cakes. That's pretty cool. We could have used a little dimensional analysis here too, right? We could have said, can I slide over? Yeah, let's go this way. We said we have half a cup of oil can make 1 cake if the oil runs out first. And we have 4 cups of oil. And the question is, how many cakes can we make? So we could have used dimensional analysis to solve this. We could have said, okay, what do we want? We want to know how many cakes. So how many cakes is what we want. What do we know? What are we given? 4. We're told we have 4 cups of oil. And now we need a conversion, now we need a conversion factor. I'll change cups of oil into cakes. And here it is. It's the recipe, the chemical equation. It says for every half cup of oil, you can make 1 cake. And then our units, cup of oil, cancels out. And all we have to do is multiply 4 times 1, which is 4. There's nothing here. That's kind of counts as a 1. Then the denominator, we have a 1/2. So 4 divided by 1/2. If you remember, gosh, what was the expression? Get your bottom right outside. Get your bottom to the right outside. I forget the little way to remember how to do this. But if you're dividing by a fraction, you actually flip it upside down and multiply it. This becomes 4 times 2, which is 8. Or put in your calculator. 4 divided by 0.5 is 8. Anyways, that's how you could use dimensional analysis instead of my silly little, trial and error method of figuring out that 4 cups equals 8 cakes. Anyways, 8. If you have infinite number of cake mix boxes, infinite amount of water, infinite number of eggs, you can use up all 4 cups of oil and make 8 cakes. Cool. How about a dozen eggs? Well, that's 12 eggs. And the recipe says you need 3 eggs to make 1 cake. So what if I multiply both sides by 4? So that'd be 4 times 3 is 12. 12 eggs can make 4 times 1, 4 cakes. Yeah, I'm more visual. So let's take these 12 eggs and put them into groups of 3. So 1, 2, 3 eggs, 1, 2, 3 eggs, 1, 2, 3 eggs, 1, 2, 3. All together, there are 12 eggs here, and each can be used to make a cake. 4 cakes can be made. And now we have enough information to figure out the problem. If I have in my kitchen half a dozen cake mix boxes, they can make 6 cakes. Water doesn't limit it. 4 cups of oil can make 8 cakes, but a dozen eggs, that can only make 4 cakes based on this recipe. So the maximum number of cakes I can take to my volunteer activity is 4, unless I run out to the store and buy more eggs. The eggs are going to run out first. Eggs are limiting the number of cakes I can make. Or you say eggs are the limiting reagent. Does that make sense? Yeah, just kind of figuring out based on the recipe. Take each one in turn. How many cakes, how many products can you make based on the quantity of each reactant? And what you do is the answer is the least number of products. So the cake mixes could make 6, the oil could make 8, the eggs can only make 4, 6, 8, or 4. You take the smallest quantity and that's the answer. Yeah. Now, there'll be some limiting reagent problems in the future. And if you don't have the recipe or you decide to ignore the balanced chemical equation, you may not get the right answer, right? Because if you look at 1/2, 4, and 1, or you look at 6, 4, and 12, well, 1/2 is smaller than 1, 4 is smaller than 6. Yeah, you would have said, you can't just look at these numbers to decide which one is limiting. No, it turns out it's the eggs. So you definitely need to go back and independently look at the balanced equation, and for each reagent, figure out how many product molecules, how many cakes in this example, can each one make. And the one that makes the fewest amount is the correct answer. That is your limiting reagent. And we stop at 4 cakes in this example. Cool. All righty, let's look at a real chemistry type question. Suppose someone mixed 0.70 grams of H2 and 75 grams of I2. How many grams of HI could be made from this reaction mixture? And remember, we just said, can't look at the initial quantities, right? Can't look at these numbers to decide which one's limiting. You need the balanced chemical equation. You need the recipe. So you can't just say, oh, this is smaller, 0.7, then so that must be limiting. No, you need the balanced equation. There's only 2 reagents. One of them is limiting. So you got 50-50 shot if you want to guess. But don't put your grade up for, to a random choice. No, let's solve the problem. Besides, I give you points for showing your work. Let's actually figure this out and get the right answer and get all the points. Okay. So how many grams of HI could be made from this reaction mixture? It depends on which one runs out first. So calculate grams of HI from hydrogen. So let's assume you have an excess of I2. You have as much as you need. How many grams of product can be made from just this quantity of hydrogen? And then repeat the calculation with the other reagent. Then calculate grams of HI from I2. So do the opposite. Now, pretend that 75 grams of HI is going to run out, and you have an infinite number, as much as you need of H2. You have an excess quantity of hydrogen gas. So you can use up all 75 grams. Well, how many grams of product, hydroiodic acid, HI, can you make? And the answer is a smaller quantity. The smaller amount. Right? That was how we did the cake analogy. We said, okay, half a dozen cakes made 6, oil made 8, eggs made 4, 6, 8, or 4. We took the smallest amount, 4. That was the answer. The eggs were the limiting reagent, and the answer was you can only make 4 cakes. So let's just do the same thing up here. We're going to need to do a little more stoichiometry, so go back and review that video if you want some help on the calculations, but I'll walk you through it right now. Okay, so what do we want? We want to know first grams of HI from hydrogen, and then second, brand new calculation, grams of HI from I2. So let's do number 1 first. What do we want? We want grams of HI. So I'm going to use dimensional analysis or unit conversion to solve this problem. So I say, okay, this is what I want, grams of HI. What am I given? That's the second part. I'm given 0.70 grams of hydrogen gas. Step 3, use conversion factors to change grams of H2 into grams of HI. And my thought process is, wait, grams and grams already match. I don't need to convert those. Ooh, but hydrogen gas is not a match for HI. I need to change H2 into HI. And the only way to change one molecule to another is with a balanced chemical equation. Where's the balanced equation? We need to figure it out. So we're told, mix some H2 with some I2 and make some HI. So let's find the balanced equation. Well, abbreviated equation, EQN. It says take H2, add I2, and make HI. Is that balanced? No. There's 2 H's over here, but only 1 over here. So let's put a 2 here. There's 2 I's. Oh, now there's 2 I's, 2 iodines. Now it's balanced. Cool. Okay. Turns out that one H2 is going to make 2 HI molecules. That's how we'll convert H2 into HI. Wait, but this number's in grams. The recipe, the chemical equation, has units of moles. It says that if you have 1 mole of H2, you can make 2 moles of HI. Dang it, we don't have moles, we have grams. So that's the first thing we have to do. Get out of grams and into moles. To make this conversion, you need the molar mass. Remember, that's where you go to the periodic table and look up the atomic weight of hydrogen, which happens to be 1 hydrogen weighs 1.0079 grams per mole. That's the atomic mass of hydrogen, 1.0079 AMU. But if you have 1 mole, then the unit is grams. Oh, but hydrogen gas comes in with 2, so we multiply that by 2. So there's 2.01, where's my math? 58 grams of hydrogen gas in every 1 mole of H2. That's the molar mass of hydrogen gas. Cool, so we changed or canceled out the grams H2, and now we're in moles of hydrogen gas. And now, if we're in the right units as the balanced equation, we can change moles of hydrogen into moles of HI. And the balanced equation says, well, there's an invisible 1 in front of the H2. So here's H2, put the number that's in the coefficient in front of that molecule. as your conversion factor. HI, there's a 2 here, so put a 2 up here. There's 2 moles of HI made every time 1 mole of H2 reacts. And that cancels out moles of H2. Nice. Our units that have survived so far are moles of HI, almost matches grams of HI. Gotta get out of moles and into grams. Grams per mole again. Grams per mole. Yeah, this is the molar mass. So again, go to the periodic table, look up hydrogen. The number on the periodic table is 1.079. Look up the mass, atomic mass of iodide. It's 126 point something. Add the weights of these two elements together, and you get 127.9124. And again, we did this calculation. We calculated the molar mass of hydroiodic acid in the previous video. So take a look at that if you want a little more detailed explanation. But hey, we got all our numbers here. The moles of HI cancel out. We are in units of grams per grams of HI. That's what we want. Cool. So get the calculator out, multiply 0.7 times 1 times 2 times 127.9124. Save that in the memory of the calculator or jot it down. Divide that by 2.0158. Yeah, because these are ones. And how many significant figures should we hold? Well, the first one has 2 sig figs. This one's an exact number. There's 5 sig figs here, significant figures. 2 and 1 are exact. That one's exact, and that has 7 significant figures. And we're multiplying and dividing. The rule for multiplying and dividing significant figures is your answer has the number of sig figs as the number with the fewest sig figs. That's 2. 0.70. You count the 7 and the following 0. You don't count the leading 0 because it's before the decimal place in front of your other digits. Yeah, 2 sig figs in the answer. So after multiplying all this out, I round up the 2 sig figs and I get 89 grams of HI that can be made from 0.7 grams of hydrogen gas if you have an excess of the I2. Okay, so now we start all over. Step 2, now calculate the grams of HI. Grams of HI that can be made from 75 grams of I2. And what's nice is if you show your work, you can look at your procedure and just duplicate the procedure. We're going to use molar mass, then the balance equation, and then we're going to use molar mass again. And if you don't want to memorize that, I don't really advocate memorizing that. I like figuring it out. The idea is, what do you want? Well, I need to calculate grams of HI, put it over here. What am I given? Well, the digits are 0.7 and 75, and I already used the 0.7. So now it's time to use the 75. The units of 75 are grams HI. And then cancel out the units. So get rid of the grams of HI and change them to something else. Well, what's the driving force? I need to get rid of this I2 molecule and change it into HI. And the only way to change one molecule to another is with the balance equation. But the balance equation has units of moles. So that's the thought process. Get out of grams and into moles. How do you change grams into moles? What quantity has units of grams per mole? Oh yeah, atomic mass, molar mass. Go to the periodic table, look up the weighted iodide. I didn't copy and paste the periodic table, sorry. 1 iodide atom, iodine atom weighs 126, sorry, 126 point something. Where's my periodic table? 9045 grams per mole. but I2 weighs twice that. And so 2 times that is 253.809 for every 1 mole. That's the molar mass. 1 mole of I2 weighs 253.809 grams. Cool. That changed the grams of I2 into moles of I2. And now I have the right units for the balance equation. Get out of moles of I2 and make them moles of this molecule, HI. Well, what's the recipe say? It says that every 1 mole of I2 will make 2 moles of HI. Every 1 mole, that's the number in front of I2, every 1 mole of I2, the number in front of 2 HI, will make 2 moles of HI. Nice. Cancel out the units of moles of I2. Now we have units of moles of HI, almost a match with grams. So finally get out of moles of HI into grams of HI. The units of grams per mole is molar mass. And hey, we already have it. The molar mass of HI is right up here. It's 127.9124. Cool. So I just grab this number and use it again. Now I get the calculator out. 75 times 1 times 2 times 127.9124. Yikes. All divided by the answer of 1 times 253.809. And then it looks like I'm going to use 2 significant figures because of the 75. And the number I got after rounding the 2 significant figures is 76. Okay. So there we go, got everything on the screen still. If you start with 0.70 grams of H2 and it runs out first, you can make 89 grams of HI. If you start with 75 grams of I2 and it runs out first, you can make 76 grams of HI, and you pick the smaller quantity. So that's the answer. The question was, how many grams, right? Let's scroll back up and read the question, make sure we're answering it. Whoops. How many grams of HI can be made from this reaction mixture of 0.7 grams H2 and 75 grams of I2? And the answer is 76 grams. And that's because the I2 is limiting. It makes a smaller amount of product. It only makes 76 grams of product. Hydrogen gas can make 89. Is limiting, or you could say I2 is the limiting reagent. It runs out first. You only get 76 grams of HI. Nice. Okay, one last idea for this video. Theoretically, if you run the experiment perfectly, you don't spill anything, you measure everything out correctly, you let the reaction go the right amount of time so that all the reagents have a chance to react, and then you purify it without any spilling, without anything sticking to the beaker. I mean, perfection. Then you get 76 grams. Theoretically, that's how many grams of product you can get starting with 75 grams of I2, if everything's done perfectly. Yikes, but we don't live in a perfect world, do we? Nope. All right, speaking of which, where's the next part of the last part of our video? Oh, it's over here, there it is. Okay, so theoretically, we can make 76 grams. However, well, if we go in the lab and someone's not very experienced and they only get 19 grams, the question would be, well, what's the percent yield if only 19 grams of HI was obtained? So you'll need to memorize this equation. It's not too bad. It's more of just reason it out, right? percent yield means, yield just means the quantity obtained. Yield, a harvest, it's what you picked out of the field. I'm trying to think of an analogy, that's all I got. So we only obtained 19. That's the actual amount. The theoretical amount was 76, right? Yep, there it is, 76 grams. So theoretically, in a perfect world, we could have obtained 76 grams. 19 grams actually was obtained through spilling and dirty glassware, contaminants, or maybe we stopped the reaction early before it finished. We got tired of waiting. And so now the percentage is 19 grams divided by 76 grams. Notice the grams will cancel. And so 19 divided by 76 times 100, it's a percent. You put that in your calculator, and I got the two significant figures, 25%. Didn't I? Double checking. Yes. There you go. So not too good, but you know what? If this is just a student doing the reaction the first time, we can't expect perfection. Got something. 19 grams, that's a decent amount. I know it's a quarter of what you could have gotten, but anyways, that's how you calculate percent yield. Memorize that reaction for my exams, that equation. Memorize that equation for our exams. If you forget and you put the theoretical amount over the actual amount multiplied times 100%, 76 is bigger than that, you're gonna get a number greater than 100%. And that makes no sense. So you can check your math, check your answer, just see, does logically, can I make more than 100%? No, you can't. In the lab, I suppose if it's wet, contaminated with stuff, you might actually weigh something that's a lot larger. I'm not going to do that to you on the actual exam. The actual amount, the actual yield will be a number smaller than the theoretical amount. All right, that's enough for now. See you in the next video.